Okay, today we're looking at a generator overview for a coal plant. The generator itself is capable of putting out about 625 megawatts. Right now running about 400 megawatts. Some of the quick overview screens. The reason we can get the higher output out of this unit, it has stator water cooling. We have our auxiliary cooling water, cools heat exchangers. The water in this part is very pure, deionized water, and it goes through resin beds. This water will actually go through the windings in the generator, pull out the heat. This would be a tank on top of the generator, maintains level. This unit also has hydrogen on the shell side of it. Right now running 60 psi hydrogen pressure inside the generator. It's 38 degrees Celsius. There's water detectors on the bottom of the generator shell looking for any leaks in the hydrogen coolers. So this water here goes up to the generator. There's like Tygon tubes that put the water right into the windings. The windings are hollow square tubes, so the water will circulate through and pull a lot of the heat out. That's why the water has to be so pure. If there's any minerals in the water, it can conduct electricity. The windings on this unit run about 24,000 volts. There is a hydrogen vent here. You do monitor for hydrogen. The pressure here is lower than inside the generator. So if there is a tube leak or a leak on any of the tubing, the hydrogen will flow into the system, and then it will be vented over here. So you can measure leakage. So if there is a leak, the water will not go into the generator, but the hydrogen will come out into the water system so you can vent it. This unit is critical to run. These are your flows. Like most things, 2 out of 3 trip it. There's 3 level transmitters. Any 2 of them get below the trip point, it'll trip. You're measuring conductivity, micro Siemens. Little dimin tank here. Just recirc pumps. They take the water, pump it through plate frame heat exchangers up to the unit, then it comes back out. This tank here is just your surge tank. Has nitrogen on it, since it's possible to get hydrogen back in here, so you don't want any oxygen in this system. Another screen just showing the generator temps. Got your A phase, B phase, C phases, stator slot temperatures, generator hydrogen temperature. This is your hydrogen cooler. This is inside the unit. These are the hydrogen coolers actually inside the generator. They sit on each end. There's a blower on the end of the shaft that moves the hydrogen gas through your heat exchangers. It picks up a lot of the heat. This is really cool in the rotor. The windings are cooled with water. There also is some stator cooling going on with the hydrogen. Hydrogen conducts heat very well, something like 7 times better than air, and it's so light you don't have the windage loss. So this is both hydrogen cooled and water cooled. This screen here is really important. This is the VAR screen showing megavars. This here is the megawatts. This here is your hydrogen pressure. 30 psi hydrogen, you gotta be in this range. 45, 60, you can run up to here. You're getting better cooling. Down here, if you're underexcited or bucking, you can have step iron heating. This is the actual metal in the generator's heating up. It's acting kind of like a motor. So it's taking some of the power off the line and changing the power factor on it. Up here, you're boosting, overexciting. Here you have rotor heating limited. Right now you got the megavars, 26 megavars, power factor's 1. Stator current, 1,000.2 amps. Basically that's 10,200 amps is in yours. Going to stator right now, leaving. Hydrogen pressure is 60. So this puts quite a bit of power out. You get 10,000 amps at 24,000 volts. Now that's just your exciter brush collector end. Exciter voltage 244 volts. Exciter current 3,288 volts. This looks for vibration and temperatures. You have your air coming in and warm air coming out. These are carbon brushes. Once a week you have to go through, check them, replace brushes as they wear. It's in the, used to be the exciter housing. They used to have a mechanical exciter, but it was changed to solid state. It's a little more efficient, less wear. This is the generator voltage control screen. These are the step-up transformers. They're full of oil, so you're using transformer oil to cool them. I just have one pump running on this one going to the cooler. Each phase has its own transformer. There's just one pump running. You have winding hot spots, equipment cooling failures. There's quite a few different protection circuits on this. We won't mention much. Isophase cooling. This is blowing air down this isophase duct. It's one conductor inside of a pipe feeding each transformer, stepped up. The unit auxiliary, this is the power the plant is using. It's taken off before the main transformers. Comes in here 24,000 volts, stepped down to 7.2 kV. So all the motors in the plant are 7.2 kV, or 7,200 volts. Get your main transformer winding temperatures. Up here we have the exciter. Same thing's running 244 volts, 3288 amps. Generator frequency. This is your breaker, static exciter. Static exciter control. You have a radio frequency monitor. This is looking for harmonics, like arcing in the unit. They can pick up weird frequencies, anything outside a 60 cycle. If you have arcing, it's going to show up as a frequency on the line. So this is looking for arcing of the generator windings. Condition monitor. This is looking for particulate and hydrogen. It takes a slipstream of hydrogen. So it's looking for particulate from insulation that's breaking down or burning. Torsional stress relays. These were taken out a while ago. This is like at 10 hertz, 20, 23. The problem with generators, there can be big swings on the line. You can get hit with very high megawatt loads, also maybe 100 megawatts is the unit in a couple cycles. What that does is basically the rotor slows way down and it starts twisting the rotor. There have been some units in the past that failed from the shaft breaking from torsional stress problems. You really don't pick it up with instrumentation, it's too quick. But there's a lot of weird things going on in the power system. We have a power system stabilizer. This has to be in service. I think it comes in about 60 megawatts. This runs the exciter and tries to take out any kind of swinging in the grid. Basically stabilizes the power. Down here we have 545 kV. We've called the transmission operator, and they want us to try to buck it. So we're going to go to the exciter voltage adjuster, and we're going to start lowering. As you can see, the amps are dropping, volts are dropping. We're actually using it for a motor, trying to bring down the high voltage on the line. Overshot a little. So basically a bigger plant like this, you can use these to balance the line voltage. If you have a bunch of small units like with wind power, solar panels, these kind of plants will actually maintain line voltage. Thought the buck and boost to maintain the voltage, whereas those small units can't really do much anything. So we got the voltage back down. Like I said, these larger generators, they don't change frequency much. They just kind of power through the spikes. If you have like a high load, somebody's energizing a line or high usage, all of a sudden the frequency will drop. So this unit can actually catch that. There's enough momentum in the turbine generator to catch that. Maintaining 60 cycles is kind of a balancing game. If you have more power than used, the frequency is going to come up. And if there's more use than power, the frequency is going to drop. So you have your balance authority operator. Their job is to coordinate with the plants how much to put out to try to maintain a uniform 60 cycle. A lot of breakers are set to trip about 58 hertz. The reason they do that, you can overflux your transformers, the high voltage and low frequency, and it creates too high of a magnetic flux. So the magnetic flux cannot go through the iron core in the transformer. It overloads it. So it looks for another path and it'll start going through the metal frame, creating a tremendous amount of heating and damage. So these are designed for 60 cycle, and they pretty much have to run at 60 cycle. And that's why your voltage is critical and your frequency is critical. You can overflux equipment and do a lot of damage. So we got our voltage down to 501. I didn't have to buck that hard. You can see up here that did change. And you can see now we're down to here. So we've dropped down. We're still quite a bit in range. We could go down to about 140 megavars for bucking. We're just minus 58 right now. So these lines here, they pretty much protect the unit, kind of show you where you're at and what you can do. Some people call it overexcited, underexcited. It can be plus, minus, buck boost. There's several different names, but the principles are all the same. Yeah, that's our quick overview of the generator operation, and we'll probably get more into the different parts of this in another video.